Welcome back, everyone. We have here highlight after highlight. Did you ever wonder what's the decision criteria for venture capitalists to spend their money in startups? They use machine learning, but what is fair? How do they decide? How is it not biased? Our next speaker, very happy to announce, is Michèle Wieland. She is a research assistant at the ZHAW, at Zurich University of Applied Science, and she's a student at statistics at ETH. So she knows all about numbers, and her real interest and passion is about machine learning and in social impacts. What is fairness, robustness? The floor is yours, Michèle.
Thank you. Thank you so much for the kind introduction. I'm really excited to be here today and to present the research which I did with my team at ZHAW and our industry partner, Raised AI. So let's get started. First, imagine we have two young entrepreneurs. The first one is a white American male entrepreneur. He just graduated from MIT with a master's. The second one is a young Indian girl. She also just graduated with a master's, but from a university in India we probably don't know. They both want to found a startup. Now ask yourself, where would you invest your money? So this toy example should illustrate biases we unconsciously have. They influence our decision and lead to discrimination against certain groups. So with this example in mind, let's start with the actual content of my presentation. Let me quickly give you an overview of what to expect from the next 15 to 20 minutes. So first, I will start with success prediction in venture capital. This was our previous research, but it's really important for me that we are all on the same page, that we can afterwards better understand the new research topic. Second, I will move on to the methodologies used in fair success prediction in venture capital. The third part will be about applying these methodology to real-world data, and the last part will be about putting fair success prediction into practice. So first, as I said, success prediction in venture capital. The first question we need to answer is, how is a successful startup defined? It's really important to acknowledge that there exist many different definitions of a success, and I will just explain the definition we used in our research. So on the slide, you see a possible funding timeline. So after the inception, a startup can receive different funding types. But of course, every timeline looks different depending on the business case and other factors. So there might be a pre-seed round, which is the very first money a company gets. It's usually their own money or from people they personally know. Then there could follow the seed round, which is the first official funding stage, and it's about taking a startup from an idea to the first step, doing some market research or product development. Usually, startups have some sort of debt financing, so just a loan from a bank. The first official funding round is called Series A funding. So it's really about building the business. The startup is expected to have some kind of first revenue and to have a business plan in hand. Along the way, there might be some grants and private equity. After Series A, they could also follow some other seed rounds, so Series B to F, which is about growing and expanding the business. So we define startup success when the company gets Series A funding. But really important, not all startups without Series A are automatically failures. So we exclude companies we're not sure about from our study. So we want to be really sure about successes and failures. So after we clarified how we define success, we need to look at which information is available to predict startup success. So we took data from Crunchbase, which is a database that provides information about companies, including startups. So there we have information about the founders. So which gender do they have? Which university degree did they get? We have information about the startups itself. So what's the company's name? Where are they located? Additionally, we have information about the funding. So what funding types did they get? What was the amount of the funding? And we also have information about the investors. It's very similar to the founders, so the personal information about the people, but we also know in which other startup did they invest. So this was a quick brush up on success prediction in venture capital, and now we're coming to the question how to predict startup success without discriminating. So here we have the same picture as before, but now we look at where are potential sources for bias and discrimination. So for the founders, we have sensitive information about their gender, race, ethnicity, or educational information. We have a similar pictures for the investors, and we have, for the startups, we have information about the country. So this could be problematic, as some countries mostly publish successful startups to Crunchbase, and this could lead to biased data. Before we can talk about how to mitigate these biases, we need to clarify how we measure fairness. There are different notions of fairness. One very well known is equal opportunity. I will just focus on a binary setting for simplicity. So equal opportunity requires that a classifier predicts a startup as successful, which is y hat equals 1, independent of the sensitive attribute, while we only focus on the true successes. I will guide you through the equation step by step. So we have failures, which are indicated with y equals 0, and we have successes, which are indicated with y equals 1. So we only focus on the successes. Among the true successes, there might be a sensitive attribute. For example, gender. So as an example, we have that 3/4 were founded by men, which is set equals set 1, and 1/4 was founded by women, which is set equals set 2. Back to the equation. We want now that the classifier predicts a company as successful with the same probability independent of the sensitive attribute, for example, gender, while we only focus on the true successes. In machine learning, we need something to optimize. So we transform this equal opportunity to the equal opportunity gap, which is just the absolute difference of the true probabilities. We want this equal opportunity gap to be as close to 0 as possible. So this notion will be our measure of fairness in the following experiments. So we've clarified now how we measure fairness, and now we look at the interesting part, namely how to mitigate biases. So we start with a state-of-the-art normal neural network. We have our input data in gray. Then in the blue part is the feature extractor. So we extract features from this input data and get a feature representation. From this feature representation, we want to predict the target. So in our case, is it a successful startup or not? One usually optimizes such a network with gradient descent. Now we add a second head to our network. This green part is responsible for predicting the sensitive attribute. The orange part we call target branch, and the green part we call protected branch. The names will be clear, I think, in a few minutes. So, what we actually want. We want a feature representation that helps us to predict the target, so the success or the failure, but we don't want any information about our sensitive attribute. How do we do that? This does not work with normal gradient descent. So we add a gradient reversal layer to our protected branch. Gradient reversal was first introduced by Gonin et al. And first used for a domain adaptation and later also for bias mitigation. So this layer flips the gradient during backpropagation. So we see there this minus lambda times the gradient. So we have an optimization problem where we want to learn our target, but unlearn our sensitive attribute. Here, for simplicity, I just illustrated one protected branch, but of course we can have multiple protected branches to protect multiple sensitive attributes. The loss of the whole network is the loss of the target branch plus the weighted sum of the losses of the protected branches. So now to the third part. Now we apply the methodologies I just explained to our data. To evaluate our results, we need to have some sort of comparison. Therefore, we have baseline model 2, baseline model 1, and baseline model 2. So baseline model 1 is just a neural network where we predict on the target, and we use our whole data set. Baseline model 2, we do the same, but we just delete the sensitive attribute from our data. So, for example, here, we cannot see it, but this should be country. We delete it from our data. But why could this be problematic? It's very likely that there are some correlation between the sensitive attribute and other features in our data. So here, as a toy example, country and currency, it's very likely that there is a correlation. So these two baseline models help us to compare the results of the FAIR models. So the first experiment. The first experiment is about protecting a single binary attribute. In our case, it's USA. It just indicates if the startup was founded in the US or not. So here on the left plot, you just see the target prediction for the three baseline models, and they're very similar. So we don't decrease our predictive performance with the FAIR model. The second picture, we take the feature representation of all three models, and we add a head to predict the sensitive attribute. This helps us to understand how much information is still hidden in the feature representation for the target prediction. So we can see here that the blue model and the green model are very similar. So to remember, the baseline model 2 is where we just delete the sensitive attribute. So it's not enough to just do that. Only with our FAIR model, the red model, we can decrease the information about the sensitive attribute in the data. So to summarize, it's not enough to just delete the sensitive attribute, and in our case, we achieve similar predictive performance for the target. The second experiment is about protecting a categorical attribute. This means the attribute has not only 2 levels, it can have multiple levels. So we did this for gender, which has 3 levels. The first level indicates that the founder team has mixed genders. The second level indicates that the founder team has only female founders. The third level, only male founders. And here we have a mix from the 2 pictures from before. So the blue line shows the target prediction of the FAIR model, which is very similar to the other models. Then we have the dashed lines, which show the predictive performance for the sensitive attribute, so for gender, from the feature representation. And the purple line is just the average of the 3 dashed lines. So we see there is not much information about gender in the feature representation used for the target prediction. So we can extend this to protect multiple sensitive attributes. So here on the slide, you see baseline model 1, baseline model 2 in the table, and then you see FM underscore country and so on, and at the bottom FM. So FM underscore country indicates the model where we only protect the sensitive attribute country. And the model at the bottom, so FM, is the model where we protect all sensitive attributes, which we defined, at the same time. So what we can observe here is that when we protect only one sensitive attribute, the average equal opportunity gap over all sensitive attributes can increase. So we have AUC, and we have equal opportunity gap, which is averaged over all sensitive attributes. So this means we need to protect all sensitive attributes at the same time, and so we achieve the best result in terms of fairness for the model at the bottom. And still, the predictive performance is quite similar to the other models. So now we're coming already to the last part of my presentation, which is putting fair success prediction into practice. So to summarize, we've seen that it's not sufficient to simply remove sensitive attributes from our data, as there might be some correlation between the sensitive attributes and other features. Therefore, we need to use a mitigation technique. One possible approach, there are of course many other approaches, but one possible approach is gradient reversal, which is used to improve group fairness. In practice, it's really important that experts determine which sensitive attributes they want to protect, as this requires background knowledge. Of course, we can always protect all sensitive attributes, so all attributes, but we also want attributes which help us to increase predictive performance. Last but not least, there could be a trade-off between fairness and accuracy. This was not the case in our scenario, but this could happen in other cases. If this happens, again, the users or the main experts need to decide how much they value fairness over predictive performance. So this was my presentation, and I'm really happy to answer all your questions and to discuss anything you want.
Thank you very much, Michèle. Are there questions from the audience? We have a microphone. There is one, thank you. Maybe I intersect quickly. So it seems to be very fair, or there's still human decision to make it fair. If I am a ruthless investor, what would you recommend? Does it outperform? Should I care? Or I just want to maximize my profit?
I think if you just want to maximize your profit, maybe fair success prediction is not for you. But as I said, there are also problems in the data. So we have biased data with the countries. There are some countries which mostly publish successful startups. And if you just use this model, this is maybe not good for your investment.
Thank you. Stoff.
So thanks, Michèle, for this great work and then the great presentation. I have two questions. One is about the weights. I mean, you said this is a trade-off. Somehow you trade it off with the weights. Maybe you can comment on that. And the second question is, I was wondering whether you have compared your results in terms of let's say, accuracy and fairness with standard approaches from post-processing. I mean, they are probably know that they're let's say, classical results, how to do that by post-processing. Is wondering whether you have done that and what you learned there.
So the first question, with the weights for the sum, so the loss of the whole network is the loss of the target plus the weighted sum of the losses of the protected branches. And as you said, these weights can be used to balance this trade-off. I don't think this was a problem in our case. We have so many features, I don't think it's a problem. But if this could happen, you could increase the weight for the target or decrease the weight for the protected branches to define this trade-off between fairness and accuracy. But from my experience, it's not trivial to do this. It's not you increase and this will happen. It's really it also depends on the complexity of your optimization task. So some of the optimizations are more easy than others. So I think it really depends on the case. And the second
Whether you compare that with
sorry.
post-processing approaches.
We haven't done that. That could be really interesting to continue our work. I think there are really like simple approaches as threshold optimizer, for example. So I think this could be a really good next step to continue the work.
Thank you.
You use here the gradient reversal for mitigating the bias, but you have a very clear the equality gap formula. Couldn't you just add that to your loss function that you try to...
Sorry, could you repeat that?
Adding the equality gap formula to the loss function and minimizing that during the training, has there been some...
Yeah, that could be a next step, of course, yeah. That's a great input.
Hi, thanks for the great talk. I was wondering if you get rid of all the sensitive features, did you do some work towards explainability? What features are then the most predictive for the success? First question, and how big is the data set that you've used?
So, the first question, yes, we did this in our previous research, which I talked about in the first chapter. So we have a paper there, which I think I linked it at the end. And there we did some analysis which features are most important, but I don't think it was very clear. It's a really high dimensional data set. So I don't think we can clearly say this attribute is the most important one. I think it's always a mix of different things. And there are I think they influence each other, so it's not that easy to say this. And what was your second question? The data set is about 40,000 startups. So we excluded a lot of them. So as I said, we want to be really sure. We could have taken much more companies, but I think when you have that many data points, it's really important to be sure about your target and failure.
Thank you for the great talk. Yes, I have a following question on the data you're using. If I look at Crunchbase or similar data sets, I might find that the majority of data points may be for the first characters that you mentioned, the guy from MIT. Are there many young Indian women founding startups which are on Crunchbase, whether they win or fail with the startup?
That's a really great point. I think this is really a problem. We train on historical data, and there, of course, we have a gap between genders. And I think this is really important. But then, we have much more information about the startup which were founded by men, so we can more accurately say something about them. But it's really difficult for the startups that were founded by women. So I think that's why it's really important to do this work.
May I just add? I was, in terms of explainability, what happens frequently in these fairness things is that the prediction algorithm works differently for different groups. And coming back to your point, I mean, it might be reasonable to think that it might, let's say that the prediction is kind of optimized for the MIT guys, but might just work poorly for the Indian women. Did you have a look at how the prediction without fairness consideration, the original one, your baseline model 0, behaves in terms of accuracy or for different groups?
So we did some analysis on which percentage did the classifier predict the startup as successful if it was founded by women, if it was founded by men. So we looked at the different groups and we saw some biases there, and this, I think, inspired us to do this work. But I think we can do more work there, especially I also think about robustness. So I think in these high dimensional setting, it's really depending on the data and maybe the case, what the classifier says. So I think this can also be improved, that we have an individual fairness and robustness.
Thank you very much. I think it's a really interesting topic and a lot of curiosity. Everyone wants to know what are the success factors. A warm thank you to Michèle Wieland, and here the nice
Thank
bottle.
you so much.